Hey guys, welcome back to another video, and this will be my first video with my voice in it. So this video will be about row echelon form and Gaussian elimination. So row echelon form is a useful form of a matrix that has lots of uses, such as solving systems of equations. Gaussian elimination is the process that's used to get to row echelon form. It's sometimes called Gauss-Jordan elimination, but that is slightly different. That's an extension of Gaussian elimination that is used for solving for row reduced echelon form, which we'll get to later. So how do you identify if a matrix is in row echelon form? A matrix is in row echelon form as long as it satisfies two conditions: that all zero rows are at the bottom and that the leading entry of every row is to the right of the leading entry above it. And if you don't know, leading entry is just the first non-zero entry. Some linear algebra classes might not distinguish between row echelon form and row reduced echelon form, which we'll call RREF. But for most purposes and ours, row echelon form only requires these two conditions. So let's get an example of what a matrix in row echelon form looks like. This matrix has a zero row at the bottom, and the leading entry of each row, which are these four in this diagonal, are to the right of the one above it. Like this one's to the right of this, this one's to the right of this, and so on. So this one is in row echelon form. This one, however, has two leading entries in the same column. This one is not to the right of this one. So this one is not in row echelon form. A matrix is in RREF, or row reduced echelon form, if it satisfies the following conditions. It has to be in row echelon form. The leading entry of every row is a 1, and every entry above the leading entry is a 0. The process of getting to row echelon form is called Gaussian elimination, which is not to be confused with Gauss-Jordan elimination, which is an extension of Gaussian elimination. It converts to RREF, not just row echelon form. So Gaussian elimination is pretty simple. All it is using the elementary row operations on the matrix until it is in row echelon form, and for Gauss-Jordan elimination until it is in REF. The elementary row operations are just swapping rows, multiplying rows by scalars that aren't zero, and adding multiples of rows to other rows. So let's get the matrix 2, 1, 3, 2, 3, 6, 1, 3, 5 into row echelon form. So you can see that first we subtract half of row 2 from row 3 to get this. Then we subtract row 1 from row 2, so we have these two zeros here. And finally we subtract 3/4 of row 2 from row 3 to get the row echelon form of the matrix as 2, 1, 3, 0, 2, 3, 0, 0, negative 0.25. And so we can also use row echelon form and REF to solve linear systems of equations as well. So assuming you already know how to solve systems, you would probably add the first and third equations and continue on with elimination and substitution. However, another way to solve systems is to put the coefficients in an augmented matrix and get the left side into echelon form or into REF. So you can see the steps that I went through. I won't go through them because that would take too long, but you can feel free to go through them yourself. So eventually we end up with 1, -2, 3, 0, 5, -5, 0, 0, 3 on the left side, and 7, -10, 3 on the right side. And you can see that this is in row echelon form, but we would have to substitute z and do a bunch of things to solve for the rest of the variables. So what we can do is to further solve for variables and get the matrix into REF, where you can like infer that it would be already solved. So you can see the steps again, but one thing to know, that if you just think about it, it's kind of obvious. When a square matrix is in REF, it's always the identity. And now that the left side is in REF, we can get the solution on the right side of 2, -1, 1, as you can see over here. And some terminology to remember that can be important later on. So the pivot positions are the positions in a matrix that correspond to the leading entries. So for the pivot positions of this, it would be row 1, column 1, row 2, column 2, row 3, column 4, and like so on. And the pivot columns are the columns that contain the pivot positions. So it would be column 1, column 2, column 4, and column 6. And when an augmented matrix for the systems of linear equations is in REF and it isn't a square matrix, then the variables corresponding to the non-pivot columns are called free variables, and it can take on any value, while the rest of the variables are called basic and they have a solution. And an example, you can see that the red columns, or the red variables, can take on any value. They're free because there's no pivot entry or pivot position. x1, x2, x4, and x6 have a solution. We can also use Gauss-Jordan elimination to find the inverse of a matrix. So we can create an augmented matrix with the original matrix on the left and the identity on the right. So if we get the left side into REF, which as I said before is just the identity because it's a square matrix, the right side will be the inverse. So over here we have 1, 2, 3, 4, and on the right is the identity. And we can subtract 3 times the first row from the second, and then what we can do is divide the second row by -2, and what we would get is this right here, which is almost an identity except for this 2 right here. And that's pretty simple. We just subtract twice the second row from the first and get the inverse of -2, 1, 3/2, -1/2, which I've basically memorized because like I always use 1, 2, 3, 4 as an example for the inverse for matrices. And so thank you guys for watching until the end, and I'll see you guys next time.